From a solid ball to a probability cloud, that's a pretty wild journey, right? Well, that's the story of the atom, and we're about to break down exactly how our picture of everything changed so dramatically.
You know, the answer to that question is, well, it's pretty mind-blowing. It's all wrapped up in a scientific detective story that took literally thousands of years for us to solve. So that's what we're going to do. We are going to trace this incredible journey. We'll start with this super simple idea of a solid little ball and end up with something honestly a lot weirder and way more interesting. All right, let's kick things off with part one, the blueberry muffin atom. Yeah, you heard that right. We're starting with the old school idea of an atom you can't break apart, and then we'll see how one big discovery just completely blew that idea out of the water.
So for literally millennia, the atom was just an idea. You know, you had the ancient Greeks with atomos, the uncuttable thing. Then fast forward to the 1800s, and John Dalton's like, okay, they're tiny, solid spheres. And that was pretty much the picture for a while. But then, 1897 happened, and one experiment just turned everything on its head. Enter J.J. Thomson. He's messing around with this cool piece of tech called a cathode ray tube. Basically, you zap it with high voltage and shwoop, a mysterious beam, a ray, shoots through the tube. Thomson got curious. He thought, what happens if I stick an electric field next to this thing? And what he saw was a game changer. That straight little beam, it bent. Specifically, it bent away from the negative electric plate. And, basic physics, right? Like charges repel. So this was it. Crystal clear proof that this ray wasn't just light or something. It was made of actual, tiny, negatively charged particles. So Thomson gives these particles a name, electrons. And here's the really brilliant part. He realized it didn't matter what metal he used. He always got these electrons. That meant they had to be a fundamental piece of all atoms. Which leads to a really important question, right? If atoms have these negative bits inside, but we know atoms themselves are neutral, there has to be some positive stuff in there too, just to balance everything out. And that's how he came up with this fantastic and kinda delicious sounding blueberry muffin model. The idea is simple. The whole atom is like this vague, fluffy cloud of positive charge. That's the muffin. And then stuck inside it, you've got these little negative electrons, the blueberries. I mean, think about it. This was the very first picture of what's inside an atom, a massive jump from just a plain old solid ball. Okay, on to part two, the empty space atom. Because in science, a good idea only lasts until a better one comes along. And let me tell you, the blueberry muffin model was about to face an experiment that would completely and spectacularly blow it apart. So now we've got Ernest Rutherford on the scene. He was actually one of Thomson's students. He comes up with this brilliant way to test the muffin model. He's going to take these tiny, heavy, positive particles, alpha particles, and fire them like little cannonballs at a super, super thin sheet of gold foil. I mean, we're talking just a few atoms thick. The thinking was, if the muffin model is right, these particles should just rip right through it, no problem. But that is not what happened. Sure, most of them went straight through, just like he thought, but some of them got deflected at these wild angles. And, get this, a few of them, a tiny, tiny number, bounced almost straight back. Rutherford's quote on this is legendary. He said it was like firing a massive artillery shell at a piece of tissue paper and having it bounce back and hit you. It was just impossible. An impossible result needs a radical new idea. And Rutherford had one. He realized the atom had to be mostly empty space. That's why most particles just flew right through. But all that positive charge and almost all the atom's mass had to be crammed into an unbelievably tiny, dense point at the center. He called it the nucleus. And the electrons? Well, they must be orbiting way out there, kind of like planets whizzing around the sun. And this analogy just perfectly captures the scale of what he'd found. Think about it. A whole sports stadium, and the nucleus is just a tiny ball bearing in the middle. It completely changes how you think about solid stuff, right? It turns out everything is mostly nothing. And don't let the size fool you. That tiny little ball bearing of a nucleus is insanely dense. If you could scoop one up, it would weigh 226 million tons. It's just mind-boggling. All the substance of the atom is packed into this one microscopic point. Okay, so this planetary model is brilliant, but it has one fatal flaw, a huge one. See, the physics of the time was very clear. An orbiting electron should be constantly giving off energy.
As it loses that energy, it should spiral inwards and, bam, crash into the nucleus. The whole atom should collapse in less than a second. But obviously they don't. This puzzle was about to lead us into the truly strange world of quantum mechanics.
And that brings us to our third and final act, the probability cloud atom. And believe it or not, the clue to solving this whole collapsing atom mystery came from looking at light, which, hey, brings us full circle, right back to those fireworks.
So check this out. You shine regular white light through a prism, you get a beautiful, smooth rainbow. But if you take the light coming from a tube of, say, super energized hydrogen gas and do the same thing, you don't get a rainbow. You get just a few sharp, specific lines of color. It's like a barcode. And every element has its own unique barcode. This was the key. It told scientists that electrons could only have certain specific amounts of energy and nothing in between. This is where Niels Bohr comes in with a brilliant idea. He pictures it like a staircase. He said an electron has to be on a specific step or energy level. It can be on step 1 or jump to step 3, but it can never hang out in the space between the steps. To jump up, it has to absorb a perfect little packet of energy. And when it falls back down, it spits out that same packet of energy as a little flash of light, a photon, with a very specific color. And those are the lines we see.
And Bohr's model was amazing. It worked perfectly for hydrogen, which has just one electron. The moment you tried it on anything more complex, the whole thing fell apart. So science needed an even deeper, even stranger answer. And this is where the big guns, Schrödinger, Heisenberg, and others, come in and invent a whole new field of physics, quantum mechanics.
Okay, so get ready, because this is where reality gets really weird. Quantum mechanics basically takes Bohr's nice, neat orbits and just throws them out the window. It says you can never know exactly where an electron is. Instead, the best we can do is define a 3D region of space, this kind of cloud, and say the electron is probably somewhere inside this cloud. We call this cloud an orbital. And that's the heart of Heisenberg's uncertainty principle. It's not that we just need better tools to find the electron. No, it's a fundamental rule of the universe. The atom isn't a mini solar system at all. It's a nucleus surrounded by these fuzzy, beautiful, three-dimensional clouds of probability, each with its own unique shape and energy level. And this brings us right back to the beginning. Those incredible, brilliant colors you see in fireworks? That's it. That's quantum mechanics in action. It's the light that gets shot out when electrons make these instantaneous quantum leaps from one probability cloud to another. All that beauty is powered by pure quantum weirdness. So there you have it, the story of the atom. We went from a tiny, solid billiard ball to a miniature solar system, all the way to this beautiful, ghostly cloud of pure possibility. It kind of makes you wonder, doesn't it? If the very bedrock of our solid, predictable world is built on nothing more than uncertainty and probability, what does that say about reality itself?